time to do some practice with problems involving implicit differentiation. And so this is a very nice idea. Once you get the hang of it and you remember to think of, okay, let me make sure I'm thinking of one variable as a function of the other variable, you'll see these problems are actually kind of fun and they're not so hard to work with. Now, let me be really implicit about this. You should be doing as much as you can on your own first, and you should really be using these videos as a supplement to your own studies. So, when you're watching, if you haven't finished a problem yet, make frequent use of that pause button. Only go up to the point where you're like, aha, this is where I was stuck. Unstuck yourself, and then keep going by your own, and try to get as much done as you can. The more practice you do, and the more that you do by yourself, the better you're going to become. Because math is like learning to play the piano. You don't become great at learning to play the piano by listening to piano recordings. You become great at playing the piano by starting with your basic chopsticks and then working your way up slowly by slowly. And it takes time and it takes effort. You're doing the right thing. You're putting in the time and you're putting in the effort. Well, let's get going with these problems for today. So, our first problem. We're going to find the slope of the tangent line to the circle of radius 5 at the point 3, 4 by using implicit differentiation and writing y explicitly as a function of x and using explicit differentiation. How do your answers compare? Now, technically, I'm missing something, which is there's many circles of radius 5 which pass through the point 3, 4. So this really means the circle of radius 5 centered at the origin. All right, so we'll make a little bit of note here, a little bit of asterisk here, centered at the origin. All right, good. Now we actually have a problem that we can make progress on. Oh my gosh, my handwriting is terrible. That's supposed to say origin. All right, well, let's begin. So our picture here is we have a circle of radius 5, and so here it is. And the nice thing about this circle is that there's some convenient points. So 3, 4 happens to satisfy that it's distance 5 away from the origin. Because 3 squared plus 4 squared, 9 plus 16 is 25, and the square root of 25 is 5. So it would be close to over here. So here's the point 3, 4. And so we're after the slope of the tangent line. We don't actually have to find the tangent line. We need to find the slope of the tangent line. Now, if we sort of do a quick eyeball it in here, what can we say? Well, it should be a negative value. Okay, is it a steep or is it less steep? I mean, what can we say about it? Well, we'll think about that as we move along here. Okay, so we're actually going to do this by two methods. Not because, one method works and the other method doesn't. We're going to get to the end. How do your answers compare? They have to be the same. If they're not the same, we've made a mistake, because it's not that like, oh, one method will give you a right answer, one method will give you the wrong answer. It's that both methods, if they give an answer, it'll be the correct answer. But what we want to see is sort of say, okay, let's look at the process. Which one was more enjoyable? Because we want to figure out, hey, let's do the thing which is a more straightforward process and we have more fun. In particular, we want to do the process which is less likely for us to make a mistake, because our goal is to try to minimize mistakes. I don't want to say our goal is going to be eliminate mistakes, because let's be honest, it's going to be tough to eliminate mistakes, but we should try to make fewer and fewer. There's a wonderful poem by a Dutch sort of polymath. There's a term called polymath. It means someone who was good at many, many things. Also good at math. Piet Hein. And he said, the road to wisdom, well, it's plain and simple to express. Air and air and air again, but less and less and less. That's what we're going for. All right, back to our story. So let's talk about our first method, method 1. Okay, so where does method 1 begin? Well, method 1 says, let's start with what we know about the circle. Now, it's the circle of radius 5 centered at the origin. So x squared plus y squared equals 25. So x squared plus y squared equals r squared. And the way that we think about doing implicit differentiation, recall, is we're going to say, let's think about what's true. We're going to have a little bit of a thought bubble here. And our thought bubble says, well, I'm going to think of y as being a function of x, but I'm not going to actually explicitly figure out what it is, because that's not the way implicit differentiation works, and because in some cases you never can figure out explicitly what it is. But I'm going to think of it. I'm going to be, and then there's a little thought bubble coming off to my side. Y equals y of x. All right, so here we go. So what do we do? Well, we're going to take the derivative of both sides with respect to x. Why? Well, because we're after the slope of a tangent line, and we think about the slope of the tangent line means the derivative, dy dx. So the derivative of x squared is 2x. The derivative of y squared. See, some people might say, oh, the derivative, there's no x there, right? Because it's a y. But remember, in our mind, we're saying, oh, y is a function of x. So there is an of x, we just don't explicitly write it down. So do the chain rule. 2y to the 1 times the derivative of the inside, which is derivative of y, and we can write that dy dx. Okay, equals, on the other side, derivative of 25. 0. Don't forget, you got to take the derivative of both sides. You can't just be like, oh, I'll take the derivative of this side, and I won't take the derivative of that side. They're no longer going to be equal unless you have some weird fluke going on. And let's not count on weird flukes saving us. Now, this gives a relationship which works for any x and y. Remember, we're after a very specific point, 3, 4. So, next what I'm going to do is plug in the point 3, 4. See, I have a choice. Do I evaluate or do I simplify? So here I'm going to just evaluate. So what do we have? We'll have 2 times 3, so 6, plus 2 times 4, 8, times dy dx. And I should say this really dy dx, I'm gonna abuse notation and keep writing dy dx. Technically, it should be evaluated at the point 3, 4. But oftentimes, I'm not going to write that down. So just understand that once I plug in, it's not the derivative at an arbitrary point, it's the derivative that's been evaluated at that point. I'll do it for this problem, but keep in mind, I probably won't do it for other problems. Now, what do we do? Well, we can subtract 6, divide by 8. So we get that the derivative at the point 3, 4 is equal to minus 6 over 8, which is negative 3 over 4. Okay, so that kind of agrees with what we're thinking of. It should be a negative slope. And if you think about where the point 3, 4 is, it should be not very negative. In other words, it should be more of a shallower slope. It shouldn't be steep. So a steep one would be if I was near the edge here. I would expect something shallower if I were near the top. And I am closer to the top than I am to the side. And so it should be more of a shallower slope. So negative 3/4, that seems like a good, reasonable answer. And so that's the slope of our tangent line. And remember, we were just after our slope for now. So that's good. So that's method 1. Now, method 2. What is that going to be? Well, let's try it out. So method 2 says, let's write y explicitly as a function of x. So we say, all right, well, x squared plus y squared equals 25. We say y squared equals 25 minus x squared. And now we're going to get rid of the square, which means we have to take a square root. Here's where we have to pay attention. Where are we in the circle? So we're in the top half of the circle, which means I need to make sure I take the positive square root. If we had been in the bottom half of the circle, we would make sure to take the negative square root. So you got to pay attention. So in our case, y is the positive square root 25 minus x squared. Or, since we want to make things more calculus friendly, 25 minus x squared to the 1/2 power. Now, let's take our derivative. All right, so I could say dy dx is what? Well, so chain rule. 1/2 comes down, 1/2. 25 minus x squared, subtract 1. 1/2 minus 1 is negative 1/2. Multiply by the derivative of the inside. So here, multiply by Derivative of 25 minus x squared would be negative 2x. All right. And, well, we could simplify this if we wanted to. For example, we can cancel the 2's. There's a half and a 2. And so I can write it as negative x upstairs. And this negative exponent means I can write a square root of 25 minus x squared downstairs. Okay, so that's my derivative. Now I need to evaluate. So I'm at the point 3,4, and since I've written it as y as a function of x, I'm going to plug in the x coordinates. I'm going to plug in x equals 3. So dy dx at x equals 3 would be negative 3 over the square root of 25 minus 3 squared, which is 25 minus 9. So that turns out 25 minus 9 is 16, and square root of 16 is 4. So minus 3/4. Okay, good. And what do you see? You see they're the same. Now, which one is better? Well, it's not so much that one is better than the other, because they both produce the same answer. And so in that regard, they're both good. Which one is better might be which one is easier to carry out the computation. And in that respect, I do think that implicit differentiation is a better method. And it's certainly more universal. See, here when we took this square root, there was a moment where we had to think, okay, are we on the positive side? Are we on the negative side? We had to pay attention. That never had to happen with implicit differentiation. It was automatically built into the expression. Now, I just want to point something out here. Do you see this part here, this piece right there? See, if you simplify, you could say, hey, square root of 25 minus x squared, that was our y. So this ends up being negative x over y. If you had come here, see, we plugged in 3,4. If you had come in here, and instead of plugging in first, you had evaluated, what you would get is you'd get dy dx. So you'd subtract 2x divided by 2y. The 2's cancel, and you'd be left with negative x over y. So that you'd end up essentially at the same place either way. But of course, this is a very special case where we can actually solve for y as an explicit function of x. In many, many cases, we will not be able to do that. So, okay, good. But this is good. It confirms our belief that it can be consistent, which we want it to be consistent. All right, on to our next problem. So, find dy dx given y cubed plus e to the power xy equals 1. All right, good. So, straightforward, we're just finding the derivative, and let's go for it. Remember, what are we thinking of? And so, whenever we see these types of problems, we always are like, and we say, I'm going to think of y as a function of x, which means that, and again, we don't write this down explicitly every time, but in our mind we're thinking of it. What we really have here is that this is y of x cubed plus e times e to the power x times y of x upstairs equals 1. Now, I don't know what y of x is. I can't solve for y of x, and I never will. Not because, I'm lazy. It's because I can't. It's just, this is one of those things where you can't do it. And mathematicians know there are certain things that cannot be done in a nice, explicit way. That's okay. We can still answer questions about these things. So this is what we're thinking of. So this is what's going on in our mind. Now, on pen and paper, we just keep going. Okay, so we have y cubed plus e to the xy equals 1. So we take the derivative of both sides with respect to x. We know it's with respect to x because of the dx. That's what tells us we're taking the derivative with respect to x. So where does x show up? Well, it shows up here because there's a y of x, and it shows up twice up here because the x and the y of x. So chain rule, the derivative of y cubed, 3y squared. 3 comes down, y to the 1 less power, times the derivative of the inside. The derivative of y with respect to x is, that's right, it's the derivative of y with respect to x, dy dx. See, it's very easy to remember that. Plus, and then here you'll have, again, a chain rule. e to something. The derivative of e to something is e to that something times by the derivative of something. And here we have x times y. That means multiplication, which means product rule. The derivative of the first times the second plus the first times the derivative of the second. And that's our derivative of the left-hand side equals the derivative of the right-hand side, which is 0. By the way, you don't always have a constant on one side. You can always make a constant on one side, because what you can do is if you have expressions on both sides, you can say, let me subtract this over. So you can always set something equals 0 by rearranging, by doing subtraction. Now, we're not done yet, because what did it ask us to find? It asked us to find dy dx. Currently what we have is an expression which involves a dy dx. So the next thing for us to do is to say, all right, we need to take the things which have a dy dx, namely it shows up in two places here, and we need to get them by themselves. So at this stage, what we're going to do is we're going to expand out. We're going to group everything with dy dx on one side. Things without dy dx go on the other side. So again, there's two sides, with dy dx, without dy dx. And this is important. You will always be able to do this. If you're not able to do this, a mistake has been made. You will always be able to carry out the next step faithfully. In other words, you'll always be able, okay, let's carry it out and let's just talk about what we mean by you'll always be able to get to this. So I'm going to multiply this through and So we get our 3y squared dy dx plus, here we'll have y e to the xy plus x e to the xy dy dx equals 0. Now, we're going to keep the terms with dy dx on one side. The term without dy dx goes across. So we'll get to the stage where we have 3y squared dy dx plus x e to the xy dy dx is equal to y e to the xy. Now, I said we'd always be able to get to the following situation, and here's what I mean, where you have all the terms on one side have a dy dx that can be factored out. If you are unable to factor out dy dx after moving stuff around, a mistake has occurred. So go back and check your derivatives. So what do we have? We have 3y squared plus x e to the xy times dy dx is equal to y e to the xy. And lastly, we get the dy dx by itself. So we divide, and therefore we can say that dy dx is equal to the ratio y e to the xy, divide that by 3y squared plus x e to the xy. And that's the expression for the derivative. So if you give us any value for x and y which satisfies the initial relationship, then we can tell you here's what the derivative is with respect to x and y. So essentially we can tell you what the local behavior is doing at that point on our curve. All right, good. Hey guys, I can't believe it. I just spotted a mistake. I know, it's like, what? I've spotted many more than that, Steve. Okay, but here's my mistake. Do you see how I brought this y e to the xy? I said move it across. If we're going to move it across, what should we have done? It should have come across as a negative. So there should be negatives here. Oh my gosh. See, that's why, look, like I said, you'll never outgrow your mistakes, but you learn to spot them, and then you can do a little bit better job. Okay, so don't forget, when you move stuff around, you put negatives in. All right, lesson learned. Good. Keep going. Well, let's try another problem. Okay. Now, find the tangent line to the implicitly defined curve x cubed plus y cubed equals 9xy at 2, 4. We should be a little bit careful here and actually ask the question, is the point 2, 4 on the curve? Now, if they ask you to do it, it should be on the curve, but you should always check. So how do we check to see if this point satisfies this relationship? Well, we plug it in. So this would be 2 cubed. All right, so 2 cubed plus 4 cubed. Does that equal, question mark, 9 times 2 times 4? Well, 2 cubed is 8. 4 cubed, 64. 9 times 2 times 4 is 72. And yes, it does work. Okay, so the point 24 is a point on the curve, which is good to know. It's not part of doing the problem, but it's good to check. You'd be surprised how many people write problems and they forget to check whether or not the point is actually on the curve. It happens. It happens. Okay, now we're going to find the slope of our tangent line because, of course, remember, if you need a tangent line, you need 2 pieces of information. One of them is a freebie. We've been given the point. We don't have to go looking for the point. We've already found it. See, look, here it is. I found it. Woohoo! There's our point. Now, so that means that we've got to do something to get the slope. So the slope is, we're going to do it in 2 ways. And so remember, we talked a little bit when we did our overview. There's the idea of you have to solve for dy dx and you have to do the evaluation. So the question is, which one do you do first? So we'll do it in both ways just so you can have a flavor of how does it feel to do it in 2 different ways. Okay. And then, just as a freebie problem, because they said, look, we need you to do a little bit more work. We don't want you to have it too easy. It says also find the normal line. All right. Well, let's begin, right? Okay. So we're going to still take our derivative. So let's go ahead and do that. All right. So derivative of x cubed. So remember, we're going to think of y as a function of x. We're going to stop drawing our picture where we have our little thought bubble. So it's like boop, 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 boop. Y is a function of x. So here we go. Derivative with respect to x. Derivative of x cubed, 3x squared. Derivative of y cubed. Well, do the chain rule. 3y to the 2 times by the derivative of the inside, which is the y function, which is dy dx. I'm going to go ahead and write this as y prime. So remember, when we write y prime, it's shorthand notation for dy dx. Okay, you're allowed to do that. And I just want to do it once just so you can see, oh yeah, we are allowed to do that. It does work. Is equal to, on the other side, product rule, derivative of the first, will leave us with a 9 times the second, plus the first, 9x times the derivative of the second. Well, the derivative of y is y prime. All right, so for both steps, I should say, excuse me, for both variations, we're going to get to here. This is where we diverge. So here is where we are going to split our processes. So let's do it. Now, the first variation here was explicitly solve for dy dx and then evaluate. So I'm going to solve for dy dx, which means I'm going to rearrange. So I want to have everything with the y prime, which is our dy dx, on one side, everything without a y prime on the other. So we'll have 3y squared y prime plus 9x y prime, except it's not plus, ha ha ha, because it came across, so it's actually a minus, sorry about that, is equal to 9y minus 3x squared. We can factor out, and if we couldn't, we'd know that we made a mistake. So we would go back and check our work. And it's okay to go back and check your work, even if you haven't made a mistake. You know, it's good to say, let me review what's been done. Can I understand it now? In retrospect, at a glance, can I see, oh yeah, here's what I did. Here's the processes. It all makes sense now. So now we divide. We get that y prime. That's 9y minus 3x squared over 3y squared minus 9x. Okay, so that's the generic. That's dy dx at any arbitrary x and y. Now, what we've done is we've explicitly solved for dy dx, then we evaluate. So we get that our y prime at the point 2, 4 would be, what would it be? Well, be 9 times 2, well, that's 18, minus 3 times 4 squared. Okay, 4 squared, and 7 years ago. Wait, no, that's not right. 4 squared is 16. 3 times 16, 48. downstairs. Wait, I did 9 times 2. That's not right. Oh my gosh, I messed that up. See, this is why you go back and you check your work. It should be 9 times 4, because 4 is our y value, so it's 36 minus 3 times 2 squared, which is 3 times 4, which is 12. So 36 minus 12. Downstairs, we have 4 squared. Okay, 4 squared. So that's 16 times 3 is 48, minus 9 times 2, minus 18. 36 minus 12 is 24. 48 minus 18 is 30. Well, they're both divisible by 6, so that leaves us with 4/5. Okay, so that's our slope. So this should be our slope. Now, the good news is we have a built-in check to work because we're going to do this in a second way. So let's do it in a second way, and if we get a different answer, then we really need to go back and check our work. But let's be confident, right? Confidence is good. We should build up our confidence. Yeah, all right, so here we go. All right, and in the second way, what are we going to do? Well, we still get to, we took our derivative, so now what we're going to do is, instead of rearranging first and then plugging numbers in, we're going to plug in numbers and then rearrange. So what we're going to do is we now plug in x equals 2, y equals 4, because that's our point. So what do we have? We have 3 times 2 squared, which is 12. 3 times 4 squared, which is 48. And then y prime. Technically, it's y prime evaluated at the point, but we'll abuse our notation and not actually write it out, is equal to 9 times 4, which is 36, plus 9 times 2, which is 18, y prime. And now you see that when we start to rearrange, what happens? Well, if we subtract 18y prime, we'll get 30y prime. Subtract 12 equals 24, or y prime equals 24 over 30. Again, we end up, there's a factor of 6, so we end up with 4/5. And there's our slope. And we're done. Now, let's compare the processes. At the end, we got the same answer. Coincidence? No, not a coincidence. Why? Because we're still going to end up finding the slope. The difference is just a matter of how much work we had to do along the way. So here we were able to say, look, I'm now evaluating as soon as I can so that when I start combining things, I can combine numbers. See, at the end of the process, see how we had this 48y prime and 18y prime? Well, that's easier to say, oh, that's 30, while over here we had to say that's 3y squared minus 9x because we couldn't see, oh, how does it come together in a quicker way? The moral of the story is, when you have the option, and if it's a possibility, evaluate as soon as possible. The sooner the better. But don't evaluate before you can. There's this quote. Sometimes people attribute it to Einstein, and they say, you should make math as simple as possible, but not simpler than that. And so the idea being, you want to make sure you make things simple, but don't make them so simple that it becomes false. And so you got to pay attention. Want to make sure that the process you're doing makes the whole process as simple to do as possible, but not do something which makes the whole process invalid. Because we do want to make sure, above all else, we want to make sure we get the right answer. All right, so we're almost done. So here we go. We can now put our answers in. So for the tangent line, we know what our slope is, and we know what our point is. So we're going to take y minus our y value. See, our y value here is 4, is equal to our slope, 4/5 times x minus our x value, which is 2. If I want to do the normal, well, that's actually going to look very similar because it's the same point. It's still going through 2, 4. So it's still y minus my y value equals something, I'll come fill that in a second, x minus my x value. Now, the only thing is I have to think about what's the slope. Well, here is when we say, oh, the normal line means perpendicular. It's perpendicular to the tangent line, so I need to do the negative reciprocal. So reciprocal makes it 5/4, and negative means you put a negative in front. And there's our lines, our tangent line and our normal line. Good, good. All right, one more problem for now. There's always more problems, right? One more for now. Okay, so given that x cubed plus x squared y plus y cubed equals 1, we want to find the second derivative of y with respect to x at the point 0, 1. Okay. Wow. Well, let's do it. Let's do it. Hopefully, it's not so bad. Well, we'll find out. So, notice this notation here says we're taking two derivatives with respect to x. So if I'm going to take two derivatives with respect to x, the first thing I should do is take one derivative with respect to x. So let's take our first derivative. So we go term by term. So our first derivative, we're going to get 3x squared plus product rule, because remember, y we're going to think of as being a function of x. So the derivative of the first times the second plus the first times the derivative of the second. For shorthand, I'll write it as y prime. Plus for y cubed, derivative of y cubed. Remember, this is a y prime, not y to the 1, y prime. That is one of the dangers here. You got to be careful. Now we do a chain rule. 3y squared times y prime equals 0. Now, you do have a choice here. And I'll tell you that there are sort of two schools of thought. And the first school of thought says, hey, let's solve for y prime first. So, in other words, let's take this expression, solve for y prime, and then we'll take a derivative. Now, the second school of thought says, keep going with derivatives. So, in other words, the question is, what do you do first? Do you rearrange and solve for what you're looking for, or do you keep taking derivatives? Now, here's my take on this. I'm not going to say that one is right and one is wrong, but I'll tell you what I always am nervous about is fractions. Whenever fractions come in, it gets a little bit trickier, especially when you're going to take a derivative of a fraction, because it means quotient rule. If you solve for y prime now, you're going to get a fraction. Almost every time you do implicit differentiation, you end up with a fraction if you solve for what y prime is. And so whenever you take a derivative of that, things are going to get, for lack of a more technical term, we call it messy. We don't want things to be messy. So if you don't solve for y prime, if you keep taking derivatives, you avoid the fractions altogether. So my advice is avoid I don't want to say avoid derivatives. I almost did. That's a no-no when you're a calculus instructor. Avoid fractions. Try to keep things simple. So we're going to keep taking our derivatives. So let's go. Let's take another derivative. Derivative of 3x squared. And remember, when we say take a derivative, we're taking a derivative with respect to x. So 6x. To take the derivative of 2xy, well, product rule. So we're going to take the derivative of the first, which will be 2, times the second, plus the first 2x, times the derivative of the second, which is y prime. Plus, now we come here, another product rule. The derivative of the first, 2x, times the second, y prime. Plus the first, which is x squared, times the derivative of the second, which is y double prime. Plus, now here, we're going to have a lot of fun here. Yes, there are x's in here. So, derivative of the first, well, derivative of 3y squared would be 6y times the derivative of the inside, y prime. So where did the 6 come from? The 2 came down, so that's where the 6. Y to the first, so that's your 6y, times the derivative of y, which is y prime. But remember, there's another y prime, so there's actually two y primes here. Then plus the first, 3y squared, times the derivative of the second, y double prime, and that is all equal to 0. Okay, good. Now, what do we do? Well, our next thing is, now that we have a relationship, let's figure out what's true. So, we're going to plug in x equals 0, y equals 1. So notice, anything with an x, that's going to become 0. So that's going to become a 0, that's going to become a 0, that's going to become a 0, that's going to become a 0. Okay, 2y. Well, that's 2 times 1, so that's a 2. Here, this would become 3y double prime. Now here, this term, I need to know what y prime is. In particular, I need to know what is y prime at 0 and 1. So we're going to come into this relationship, and now we're going to plug in x equals 0 and y equals 1. So if we do that, we'll get 0 plus 0 plus 0, because all these terms involve 0, plus 3y prime equals 0, which means that y prime at the point 0, 1 is also equal to 0. So we get y prime equals 0, which says that this term is also 0. Woohoo! Yes, look at all these lovely zeros. So, lo and behold, what do we end up with? Almost all of it canceled. Not all, almost all. What didn't cancel was the 2, and then 3y double prime. So, subtract 2, divide by 3, y double prime equals minus 2 over 3. So, we can say that our second derivative is negative 2/3. And there you go. There you go. Wow, nice. Good stuff. All right, keep practicing. You're getting it. Keep going.